All right, guys, let's talk about some applications of linear equations and inequalities. So applications, that means real world stuff. That means word problems. Come on now, I know you're excited. All right, let's start with one about rate of change. The median price of an existing home in the United States was $139,000 in 2000. The median price had risen to $191,300 by 2004. Find the average annual rate of change in median home price from 2000 to 2004. So we are looking for rate of change. So the first thing I want to do is identify my independent and dependent variables. That's going to be my most important first step. So let's do that first. We have independent variable and dependent variable. Well, the independent variable here is the time in years, and the dependent variable is the cost of the houses. So that means that I'm looking for the change in my dependent variable on top and my independent variable on the bottom. So we can use the word change. I like to use the symbol, the Greek letter delta. Okay, change and delta actually mean the same thing. So the Greek letter delta is a triangle, stands for change. Change in the dependent over change in the independent. So take your dollar amounts and subtract the later one, which also happens to be the larger one, but keep in mind it will not always be the larger one because you can have a negative rate of change when there's a decrease. But in this case, it's the later one. And then on the bottom of my fraction, I'm going to put the dates, and again, later minus earlier. And we end up with 52,300 over 4. And we divide that, we get 13,075. Now remember, a rate of change has to have a unit. And this one is dollars per year. Now you could write the word dollars per year, or you could put the dollar sign in front of the amount. So what is the rate of change? At what rate was the median home price in America changing? Well, it was changing at a rate of $13,075 per year. Notice that it's positive, so that tells us that's an increase. Let's move on to a direct variation problem. The engine of a chainsaw requires a mixture of engine oil and gasoline. According to the directions, oil and gasoline should be mixed as shown in the graph below. What is the constant of variation for the line graph? So the constant of variation, let's start by thinking about what do we know about a direct variation. Well, we know the equation is y equals k times x. We know that it goes through the origin 0, 0, which often makes sense for a real-world application because if I had 0 ounces of oil, I would be mixing it with 0 ounces, or gallons, excuse me, of gasoline. So that only makes sense that 0, 0 fits there. What else do we know? We should recognize that K is the same thing as M. So that's the same thing as the slope, although that K stands for the constant of variation. Sometimes I'll write the word constant with a K just to help myself remember that K is the constant of variation. So I'm looking for the slope, the ratio of rise and run, the constant of variation here. Easiest way to do that is going to be to find the rise and the run. Now I could have used this point here, but that halfway point, it looks like it's at 2.5 for the y value, but I don't want to eyeball that. So I'm going to pick one that's actually on grid lines that I can use. So remember, rise on the top, run on the bottom. That constant of variation is the same thing as the slope of this line. So the rise here is 5, the run here is 2. Divide that and we get 2.5. You could also use 5 halves. So if I was to write the equation, it would be y equals 2.5x. If I'm just finding the constant of variation, it's 2.5. All right, the 3 forms of a linear equation. We're going to go ahead and write all 3 forms for one problem. So what are they, first of all? Let's go through and actually read the problem, and then we'll write down the forms of the linear equation first before we actually write the equations themselves. Jeff paddles his canoe at an average speed of 3.5 miles per hour. After 5 hours of canoeing, Jeff has traveled 18 miles. Write an equation in point-slope form for the first one to find the total distance y for any number of hours x. So we're starting with point-slope form. Point-slope form is y minus y1 equals m times the quantity, x minus x1. So that's my point-slope form. How do I write that? Well, I have a slope because they tell me the rate at which, the speed at which he is traveling. That is your slope here, because every hour that passes, he will have gone 3.5 times as many miles. So for 1 hour, it'd be 3.5 times 1, and that would be your y, would be 3.5 miles, and so on. So for point slope form, I need a point, x1, y1, and a slope. I've already explained we have the slope. That's the 3.5. The point we have is, remember, it's hours to distance, 5 hours, 18 miles. After 5 hours, he's traveled 18 miles. So all we do now is plug in the point and the slope. So it's y minus the y value in our ordered pair, which is 18, equals 3.5 times the quantity x minus the x value of our ordered pair, which is 5. So that is your point slope form. Now, how do I take point slope form and write slope intercept form? Well, first of all, what is slope intercept form? Well, it's y equals mx plus b. Well, m is your slope and b is your y-intercept. So that means I need to take the equation I got over here in green, right here, and make it look like this. The best way to do that is to take it and solve for y. You're going to keep hearing that. It's something we have to be able to do comfortably. So we're going to solve this for y. Well, to solve this for y, we start by distributing. So now I have y minus 18 equals 3.5x minus 17.5, 18.5, 17.5. Hold on, let me check. Yep, it was 17.5. So we're going to add 18 to each side. I apologize for the mess there. And because I'm out of space here, I'm going to write it up here. Y equals 3.5x plus 0.5. And there is your slope-intercept form of the equation. Now we need it in standard form. So finally, standard form, that's the one that's ax plus by equals c. A, b, and c all have to be integers. So we're going to take this equation up here. We need to get x and y together on the same side and do something to the equation so that we have all integers. So I'm going to copy it down. Well, let's get x and y on the same side by subtracting 3.5x from each side. And we get negative 3.5x plus y equals 0.5. And now to get rid of those decimals, let's double everything. Make it negative 7x plus 2y is equal to 1. And that is what we call standard form. Now I could write it 7x minus 2y equals negative 1, and that would also be acceptable. Both of those are equivalent to one another. The difference? Well, here the x is a positive, making everything else the opposite sign in this particular equation, because I just took this and multiplied by negative 1. So x is a positive coefficient. And over here, it's the one we found just by finishing it off. And the reason I did that, guys, is that sometimes standard form, in some textbooks, they say a has to be positive. But see, both of these, to me, work for standard form. Onward. Slope-intercept form by itself again. So the most convenient one, still slope-intercept form. Let's take a look at this particular example. A computer repair service charges $50 for diagnosis and $35 per hour for repairs. Let X be the number of hours it takes to repair a computer. Let Y be the total cost of the repair. Well, if Y is the total cost of the repair, we're going to start off with Y equals, because we are writing an equation in slope-intercept form. So Y equals what? Well, y equals, you have $50 that you have to pay, and I'm going to put that in the spot for B. So the base amount I'm paying is your y-intercept, that's your B. After that, it's $35 per hour that we work, and we know anytime we see 35 per hour or 35 per, and the hours or whatever we're saying here, that we have 35 for each one, whatever that is, that variable, it's 35 times that variable. Because for 1 hour, it'd be $35. For 2, you'd multiply and it'd be 70. For 3 hours, it'd be 105. For 4 hours, it would be 140. Okay, so there's our slope-intercept form of our equation. Let me put an A there with the answer. The graph of our equation. Well, I'm not going to make it a super special graph here. Here's 50. Put 50 there. We'll put 100 up here. On the x-axis, I'm not going to count by 50s. I'm going to count by 1s, 2s, etc. Whoops, sorry about that. I just moved the entire thing. There we go. I'm going to count by 1s, 2s, etc. So 1, 2, 3, 4, 5, 6, 7, 8, 9 hours. I would assume if you have a computer repair over 9 hours, it's probably not a good idea to repair it. Probably a good idea just to replace the darn thing. But we're not all made of money, so you know. Okay, so anyway, we're going to end up with a graph that looks something like this. So we have a rise of 35 and a run of 1. Now, I didn't use graph paper for this. I just sketched the basic graph. Now, the third question here is, why is the line only in quadrant 1? Well, that should be pretty easy to answer. Any ideas? Well, x and y can only be positive because we're talking about real-world examples here of things that are quantified. Because your x and your y can only be positive, that puts you only in quadrant 1. You can't have a negative cost for the repair. They're not going to hand you money to repair your computer, and you're not going to have negative hours because time can't pass backwards. All right. Last slide in this video. And our last application problem is a linear inequality. In 2004, the median household income or yearly family income was about $44,000 per year. Suppose the average annual rate of change since then is $1,240 per year. Write and graph an inequality for the annual family incomes Y that are less than the median for X years after 2004. So I want to be thinking here about the basic form of a linear equation. We're going to make it an inequality by having an inequality symbol instead of an equal sign. Well, Y is our family incomes here. The rate of change is our slope here. That's 1240, so that goes in the spot for M. And that's an increase because it's a positive rate of change, so it's increasing from the baseline of 44,000. In this inequality, X represents the years since 2004. So we can call this our y-intercept because this was the yearly average family income, or median, excuse me. So average, and actually, median and average can be used as synonyms. We'll talk about that as we get closer to stats. But anyway, this amount was the actual amount for the year 2004. So instead of an equation, though, we want where the incomes are less than this. So now we have to graph this. So it's not going to be a super fancy graph here, guys. On my graph, counting 1, 2, 3, 4, 5, 6, 7, 8. This is years since 2004. And on the y-axis, it's going to be family income in thousands. Okay, so here's 50,000 right here. And 5, 6, 7, 8, 9. That's not too bad, kind of even. 1, 2, 3, 4. That's not bad at all. I'm going to graph my y-intercept at 44,000, which is going to put me approximately here-ish. And I know that my slope is 1,240. So it's not going to be perfect. I'm not going to calculate exactly where I'm going here. But I go basically up by 1,000 and maybe a little bit more and over 1. Because the slope here is right here. And remember, that's 1240 over 1. Okay, so that's a rise of 1,240 and a run of 1. That's going to put me approximately here. So that's the trajectory that this line needs to take. Now, you're not going to be able to answer the rest of the problem, this part over here. Not really going to be able to do that with my graph. My graph is not detailed enough. It probably is not going to be specific enough. I'm probably going to have to write out the work for that. So, excuse me. So let's do the shading and then we'll go back and do those ordered pairs. Now, where am I shading? Well, because this is less than, I'm shading downward underneath. Now, notice I'm actually not going to think about any other quadrants here because, again, we're dealing with only positive values. So a lot of application problems, you only have the first quadrant, like we said in the previous problem. Let's look at those ordered pairs. Okay, we have a hastily copied and pasted graph. Now, the point here is what I was trying to get at on the previous screen is I can't really tell if 249,000 fits here. It could be just above, it could be just below, it could be on that dotted line. So I'm going to have to actually do these out algebraically. So let's start by writing our y is less than 1240x plus 40x plus 44,000. And now we're going to start plugging in these ordered pairs. So if I plug in 49,000 for y, does that make a true inequality with a 2 plugged in for x? And this is the benefit of a graphing calculator, because where I know that we're looking at it like, well, but now I have to write it all the way out. Well, you don't. And you might hear the little buttons being pressed as I'm going through the problem. 49,000, is that less than 46,480? No, it is not. This ordered pair does not work. And that's how you're going to go through all of them. So I'm going to pause it and write that out. You try it yourself, but I'm going to go ahead and pause it and write it out to shorten our video up a bit. And there you have it. Let's go through in color coding here. So the first one we found was not a solution. The second one, we plugged in the ordered pair. We did get a true statement because 46,000 is less than 50,200. If you look over here, 46,000 would definitely be in the shaded area. So we definitely say this is a solution. The next one in purple, we plug it in and we get a no because 53,920 is not larger than 65,000. And if you look over here at 8 years, we definitely, it does not appear that I did a very good job on this here, because that really would look like it would be, but if we look at the math, it clearly, here, it clearly is not. That is not less than that. So that's a no. So that one was a no. And then when we plugged in 10, we got a yes. Because, again, over here, we plugged in the 10, we did get a statement that was true. Okay, so a couple of applications. Hopefully you're a little more comfortable with some of this stuff. Continue practicing. Use your IXL to your advantage here, folks, and I will see you in class.